Somewhere in the depths of space, particles of antimatter are colliding with ordinary matter and unleashing the most powerful explosions in the known universe. We thought antimatter was science fiction, exotic fuel for starships and movies. We were completely wrong. Antimatter is real. It's being created constantly throughout the cosmos. And when it meets regular matter, it releases 100% of its mass as pure energy. That's not a typo. 100% efficiency. Nuclear fusion, the process that powers our sun, converts less than 1% of matter into energy. Antimatter annihilation makes fusion look like a dying candle compared to a supernova. The journey we're about to take will carry us from the practical reality of antimatter medical imaging happening in hospitals today to the theoretical boundaries where physics breaks down and philosophy begins. We'll explore how the absence of something, the missing antimatter that should fill our cosmos, tells us more about the nature of reality than all the matter we can see. And we'll confront the unsettling possibility that we're living in the debris of a cosmic catastrophe that destroyed almost everything that should have existed. Now let's begin this journey into the most beautiful and disturbing mystery in the universe. Chapter 1. Perfect Opposites. In 1928, a young British physicist named Paul Dirac was struggling with an equation that refused to behave. He had been trying to reconcile Einstein's special relativity with quantum mechanics, hoping to describe how electrons move at speeds approaching light. But every time he worked through the mathematics, something strange emerged. His equation demanded that for every electron in the universe, there must exist another particle, identical in mass, but opposite in electric charge. Dirac's colleagues were skeptical. The idea seemed too perfect, too symmetric to be real. But the mathematics was undeniable. The equation that successfully described the behavior of electrons at relativistic speeds required the existence of these mirror particles. Dirac had no choice but to predict something that had never been observed: antimatter. Think of it this way. Imagine you're looking at yourself in a perfect mirror, but instead of reflecting your image, this mirror reflects your fundamental properties. Where you have positive electric charge, your reflection has negative. Where you spin in one direction, it spins in the opposite direction. But in every other way, mass, size, the patterns of how you interact with forces, you and your reflection are identical. That's the relationship between matter and antimatter. The concept was so radical that even Dirac initially tried to avoid its implications. He first suggested that the positive particles his equation predicted might be protons, the particles found in atomic nuclei. This would mean that electrons and protons were somehow mirror images of each other, despite their obvious differences in mass. But the mathematics wouldn't allow this interpretation. The mirror particle had to have exactly the same mass as the electron, not 1,836 times heavier like a proton. By 1931, Dirac had accepted what his equation was telling him. He published a paper predicting the existence of the positron, a particle identical to the electron in every way except electric charge. Where electrons carry negative charge, positrons would carry positive charge. Where electrons are attracted to the positive nuclei of atoms, positrons would be repelled. They were, in Dirac's words, holes in the sea of negative energy. This prediction represented something unprecedented in physics. Never before had a purely theoretical calculation, divorced from any experimental observation, demanded the existence of an entirely new form of matter. It was as if the universe as fundamental mathematical structure was revealing hidden symmetries that couldn't be ignored. The implications were staggering. If every particle had an antiparticle mirror image, then there should be an entire periodic table of antimatter elements. Antihydrogen with a negatively charged nucleus orbited by a positively charged positron. Anticarbon, antioxygen, antinitrogen. The possibility of entire antimatter stars, antimatter planets, even antimatter life forms performing their own antimatter chemistry. But there was a catch, and it was devastating. Dirac's equations also predicted what would happen when matter and antimatter met. Unlike ordinary chemical reactions, where atoms rearrange but mass is conserved, matter-antimatter annihilation would be total. Both particles would vanish, converting their entire mass into pure energy according to Einstein's famous equation E equals mc. To understand the power of this process, consider that when gasoline burns in your car's engine, roughly 1 part in a billion of its mass converts to energy. When uranium undergoes nuclear fission in a power plant, about 0.1% becomes energy. But when matter meets antimatter, 100% of the mass becomes energy. It's the most efficient energy conversion process possible in our universe. This efficiency has mind-bending consequences. A single gram of antimatter annihilating with a gram of ordinary matter would release the energy, equivalent of 43,000 tons of TNT. That's roughly 3 times the power of the atomic bomb dropped on Hiroshima. The antimatter in a penny would power New York City for several days. The antimatter in a paperclip could launch a spacecraft to Mars. But here's where the mystery deepens. If matter and antimatter are perfect mirror images, if they're created by the same fundamental processes, and if they annihilate with perfect efficiency, then where's all the antimatter? The universe should be exactly half matter and half antimatter. Instead, we see a cosmos dominated almost entirely by matter, with antimatter appearing only in fleeting moments during high-energy collisions. The mathematics of Dirac's equation suggested a universe of perfect symmetry. Reality, however, tells a very different story. Every star we observe is made of matter. Every planet, every gas cloud, every speck of cosmic dust consists of ordinary particles, not their antimatter mirror images. If significant amounts of antimatter existed anywhere in our cosmic neighborhood, we would detect the characteristic gamma rays produced when it annihilates with interstellar matter. We don't see these signatures. This absence represents more than just a missing piece of the cosmic puzzle. It represents a fundamental violation of what physicists call CP symmetry, the idea that physical laws remain unchanged if you swap all particles with antiparticles and simultaneously mirror reverse all spatial coordinates. According to this principle, a universe made of antimatter should behave exactly like a universe made of matter, just running in reverse. Yet our universe clearly violates this symmetry. We exist in a cosmos where matter has won a decisive victory over antimatter, despite starting from conditions that should have produced them in equal amounts. This victory margin was incredibly small, perhaps just 1 extra matter particle for every billion matter-antimatter pairs. But it was enough. That tiny imbalance, multiplied across the entire observable universe, accounts for every atom of matter we see today. The remaining questions are profound and disturbing. What force or process could have created this subtle preference for matter over antimatter? Why did the universe's fundamental symmetries break down in just the right way to allow our existence? And perhaps most unsettling of all, are we living in the debris field of a cosmic catastrophe that destroyed virtually everything that should have existed? Paul Dirac's beautiful equation had revealed the existence of antimatter, but it had also exposed the deepest mystery about why anything exists at all. The perfect opposites his mathematics predicted should have led to perfect annihilation. Instead, they led to us. Chapter 2. Cosmic Discovery. Carl Anderson wasn't looking for antimatter when he found it. In August 1932, the young physicist at Caltech was studying cosmic rays, mysterious high-energy particles that constantly bombard Earth from deep space. His cloud chamber, a device that tracks charged particles by the trails of water droplets they leave behind, had captured something extraordinary. A particle had curved through the chamber's magnetic field in precisely the wrong direction. Anderson stared at the photograph for hours. The track showed a particle with the same mass as an electron, but bending the opposite way in the magnetic field. By all known physics, this should have been impossible. Electrons, with their negative charge, curve in predictable directions when passing through magnetic fields. This particle curved the other way, as if it carried positive charge while maintaining an electron's tiny mass. 3 years after Dirac's theoretical prediction, antimatter had announced its presence in the most dramatic way possible. The positron, Dirac's hypothetical anti-electron, was real, and it was arriving at Earth as a component of cosmic radiation from the depths of space. Anderson's cloud chamber had captured the first confirmed antimatter particle in human history. The discovery revolutionized our understanding of the universe's composition. Cosmic rays, it turned out, are massive particle accelerators operating on scales that dwarf anything humans have built. When ultra-high energy protons from distant stars and galaxies collide with atoms in Earth's upper atmosphere, they create showers of exotic particles, including antimatter. Every second, thousands of positrons rain down on our planet, most annihilating instantly when they encounter the matter-dominated environment of Earth's atmosphere. But Anderson's discovery raised more questions than it answered. If cosmic rays routinely produce antimatter, why don't we observe vast clouds of it floating through space? Why hasn't some region of the universe remained dominated by antimatter since the Big Bang? The cosmic background should contain approximately equal amounts of matter and antimatter if they were produced together in the universe's birth. Instead, we observe a cosmos that seems almost entirely constructed from ordinary matter. The implications became even more disturbing as astronomers began mapping the universe's large-scale structure. Galaxies form clusters spanning millions of light years. These clusters themselves group into superclusters stretching across hundreds of millions of light years. And nowhere in this vast cosmic web do we detect the signature of antimatter galaxies annihilating with matter galaxies at their boundaries. Consider what such annihilations would look like. When matter and antimatter meet, they produce gamma rays with very specific energies, minus 511,000 electron volts for electron-positron annihilation, higher energies for heavier particle pairs. These gamma rays would create a distinctive glow along the boundaries between matter and antimatter regions. Our most sensitive gamma ray telescopes should easily detect such signatures if antimatter galaxies existed anywhere within billions of light years of Earth. They don't. The universe appears to be matter-dominated to the very edge of our observational horizon. This absence forces us to confront an uncomfortable truth. Either antimatter was never produced in significant quantities during the universe's formation, which would violate our understanding of fundamental symmetries, or was produced but subsequently eliminated by some unknown process. Both possibilities challenge the elegant mathematical frameworks that physicists have used to describe reality. The mystery deepened as researchers began creating antimatter in laboratory settings. By the 1950s, physicists had learned to produce antiprotons using high-energy particle accelerators. These experiments confirmed that antimatter behaves exactly as theory predicts. Antiprotons have the same mass as protons but opposite charge. When combined with positrons, they form antiatoms that should obey the same physical laws as ordinary atoms. In 1995, researchers at CERN successfully created the first atoms of antihydrogen, antiprotons orbited by positrons. These antiatoms lasted only microseconds before annihilating with surrounding matter, but they represented a milestone in antimatter physics. For the first time, humans had created the antimatter equivalent of the universe's most common element. The antihydrogen experiments revealed something profound and troubling. Antimatter atoms appear to follow exactly the same rules as matter atoms. Their spectral lines, the colors of light they absorb and emit, match theoretical predictions based on perfect matter-antimatter symmetry. This means that antimatter chemistry should work exactly like ordinary chemistry, just with reverse charges. But if antimatter follows the same physical laws as matter, if antimatter stars could shine like ordinary stars and antimatter planets could form around them, then why don't we observe any? The absence becomes even more mysterious when we consider that the Big Bang should have produced equal quantities of both. The cosmic ray discoveries that began with Anderson's cloud chamber photograph have now been extended by satellite-based detectors operating above Earth's atmosphere. These instruments can measure cosmic ray composition with extraordinary precision, searching for any trace of antimatter nuclei, antihelium, antilithium, or heavier antimatter elements that might indicate the existence of antimatter stars or galaxies. The results are consistently disappointing. Among the billions of cosmic ray particles detected each year, antiprotons appear at roughly the rate expected from high-energy collisions between ordinary cosmic rays and interstellar matter. But antimatter nuclei heavier than antiprotons are virtually non-existent. The cosmic environment appears to contain no significant sources of complex antimatter. This observation eliminates one of the most hopeful possibilities for resolving the antimatter mystery. If distant regions of the universe were dominated by antimatter, they would occasionally expel heavy antimatter nuclei into intergalactic space, just as ordinary stars expel matter through stellar winds and supernova explosions. These antimatter nuclei would travel across the cosmos and occasionally reach Earth's vicinity, where we could detect them. We don't find them. The absence of heavy antimatter nuclei in cosmic rays provides strong evidence that no significant antimatter structures exist anywhere within our cosmic neighborhood, a region extending at least billions of light years from Earth. Yet the fundamental laws of physics offer no clear explanation for why this should be so. The standard model of particle physics, our most successful theory of fundamental forces and particles, predicts that matter and antimatter should be produced in exactly equal quantities. The absence of cosmic antimatter represents a glaring contradiction between theory and observation. This contradiction has profound implications for our understanding of the universe's origin and evolution. If matter and antimatter were initially present in equal amounts, some process must have systematically eliminated antimatter while preserving matter. But what process could operate on cosmic scales with such perfect efficiency that it left virtually no trace of antimatter anywhere in the observable universe? The cosmic discovery of antimatter, which began with Anderson's cloud chamber and continues today with space-based detectors, has revealed one of the deepest mysteries in modern physics. We know antimatter exists because we can create it and detect it. We know it should exist throughout the universe because the same processes that created on Earth operate everywhere in the cosmos, but we cannot find it. This absence echoes across every scale of cosmic structure, from the smallest particles raining down in cosmic rays to the largest galaxy clusters spanning hundreds of millions of light years. Somewhere in the universe's history, antimatter nearly vanished, leaving behind only the matter we see today and the profound mystery of why anything exists at all. Chapter 3. Impossible balance. Imagine flipping a coin 13,800,000,000 times and getting heads on every single flip. That's not just unlikely. It's so improbable that it effectively never happens in any universe, no matter how long you wait. Yet something equally impossible appears to have occurred in the early moments after the Big Bang. Matter won over antimatter with such decisive completeness that we observe essentially no primordial antimatter anywhere in the cosmos today. The mathematics of this impossibility are staggering. According to our best understanding of particle physics, the Big Bang should have produced exactly equal amounts of matter and antimatter. For every quark that emerged from the primordial energy of creation, an antiquark should have appeared alongside it. For every electron, a positron. For every proton that would eventually form atomic nuclei, an antiproton carrying the same mass but opposite charge. But here's where the impossible balance reveals itself. If matter and antimatter have been produced in exactly equal amounts, They would have annihilated each other completely within the first second after the Big Bang. The universe would have ended before it began, leaving nothing behind but a sea of photons rippling through empty space. No atoms, no stars, no planets, no life. Just pure energy dispersing into the growing darkness of an expanding void. Yet obviously, that's not what happened. We exist. Every atom in your body, every star burning in the night sky, every galaxy wheeling through space testifies to the fact that matter survived this cosmic annihilation. But for matter to survive, there must have been more of it than antimatter from the very beginning. The question that haunts modern physics is this: how much more? The answer reveals the knife-edge nature of our existence. Current observations suggest that for every billion particles of antimatter created in the Big Bang, there were 1,000,001 particles of matter. That extra particle, just 1 part in a billion, represents the entirety of the matter we see in the universe today. Everything else annihilated away in the first microseconds after creation, releasing enough energy to power the universe's expansion for billions of years. This tiny imbalance, what physicists call the baryon asymmetry, contradicts one of the most fundamental principles in physics: charge parity conservation, or CP symmetry. According to this principle, physical laws should remain unchanged if you simultaneously replace all particles with their antiparticles and mirror reverse all spatial coordinates. In a perfectly CP-symmetric universe, matter and antimatter would behave identically, making any preference between them impossible. The violation of CP symmetry represents more than just a technical problem in particle physics. It challenges our understanding of how the universe operates at its most fundamental level. If the laws of physics contain built-in preferences, subtle biases that favor certain types of particles over others, then the cosmos is not the elegant, perfectly balanced structure that mathematical physics seem to predict. The search for the source of this asymmetry has led physicists to explore some of the most exotic phenomena in nature. They've discovered that certain particles, called neutral kaons, can spontaneously transform into their own antiparticles and back again, creating subtle differences in how matter and antimatter decay. They found that the weak nuclear force, responsible for certain types of radioactive decay, treats matter and antimatter slightly differently. And they've theorized about massive particles that existed only in the universe's first moments, decaying in ways that produce more matter than antimatter. But none of these discoveries fully explains the magnitude of the asymmetry we observe. The CP violations detected in laboratory experiments are far too small to account for the 1,000,000,001 dominance of matter over antimatter in today's universe. Something else must have happened in those first crucial moments after the Big Bang. Some process or force that we haven't yet identified or understood. One possibility involves the Higgs field, the energy field that gives particles their mass. In the early universe, when temperatures were trillions of times hotter than the sun's core, the Higgs field may have behaved very differently than it does today. As the universe cooled and the Higgs field settled into its current configuration, it might have created conditions that favored the production of matter over antimatter. Another possibility lies in the realm of supersymmetry, a theoretical framework that predicts every known particle has a massive superpartner particle. If these superpartners existed in the early universe and decayed asymmetrically, they could have produced the matter-antimatter imbalance we observe today. However, despite decades of searching, no supersymmetric particles have been detected, casting doubt on this elegant solution. Perhaps the most radical possibility is that our universe is not unique. Some cosmological theories suggest that the Big Bang created not one universe, but many, each with slightly different physical properties. In most of these universes, matter and antimatter would have been produced in exactly equal amounts, leading to complete annihilation. We find ourselves in one of the rare universes where a tiny imbalance favored matter, simply because we can only exist in such a universe. This anthropic principle offers a disturbing resolution to the antimatter mystery. It suggests that the impossible balance we observe is not the result of any fundamental physical process, but rather a selection effect. We observe a matter-dominated universe because we can only exist in a matter-dominated universe. All the perfectly balanced universes where matter and antimatter annihilated completely remain forever unobservable, their inhabitants never evolving to wonder about their own existence. The implications extend far beyond cosmology. If our universe's basic properties, the relative abundances of matter and antimatter, the strengths of fundamental forces, the values of physical constants, are essentially random variables that take different values in different universes, then the elegant, mathematical frameworks of physics may be telling us less about fundamental reality than we hoped. Consider the profound loneliness this implies. If the matter-antimatter asymmetry that allows our existence is essentially accidental, then we may be surrounded by countless universes filled with nothing but radiation, their matter having annihilated completely in the first moments after their respective Big Bangs. We would be cosmic lottery winners, inhabitants of one of the vanishingly rare universes where the random number generator of creation happened to favor matter over antimatter by just enough to allow complexity, chemistry, and ultimately consciousness to emerge. The impossible balance that creates our reality may be impossible for good reason. In a perfectly symmetric universe governed by perfectly balanced physical laws, nothing interesting can happen. Perfect equilibrium means perfect stasis. For complexity to emerge, for evolution to occur, for consciousness to develop, the universe must be fundamentally unbalanced. The mystery of antimatter's rarity may be telling us that existence itself requires imperfection. Yet this realization brings little comfort. If our universe exists only because of an accident of cosmic proportions, if the slightest change in the initial conditions after the Big Bang would have led to complete annihilation, then our existence hangs by the thinnest possible thread. We are not the inevitable products of an elegant, symmetrical cosmos, but rather the unlikely survivors of a cosmic catastrophe that destroyed almost everything that should have existed. The impossible balance that allowed matter to survive reveals the universe to be a far stranger and more precarious place than we ever imagined. We live in the aftermath of a victory so narrow that it defies rational explanation, celebrating our existence while wondering why we're here to celebrate at all. Chapter 4. Quantum mirrors deep beneath the Swiss-French border. In tunnels that stretch for 27 kilometers through solid rock, scientists are performing acts that would seem like magic to any previous generation of humans. They're creating antimatter. Not just individual particles like the positrons Carl Anderson detected in cosmic rays, but entire atoms of antimatter, captured, studied, and manipulated with precision that borders on the miraculous. The Large Hadron Collider, the most powerful particle accelerator ever built, routinely produces conditions that existed nowhere in the universe since the first microseconds after the Big Bang, when protons collide at energies approaching the speed of light. They create showers of exotic particles that exist for mere fractions of a second before decaying into more stable forms. Among these ephemeral creations are antiprotons, the antimatter mirror images of the protons that form atomic nuclei. But creating antimatter is only the beginning. The real challenge lies in capturing it, studying it, and comparing its properties to ordinary matter with exquisite precision. This requires technologies that push the boundaries of what's physically possible. Antimatter cannot be stored in ordinary containers. It would annihilate instantly upon contact with any material surface. Instead, scientists use magnetic fields to trap individual antimatter particles, suspending them in perfect vacuum for hours or even days. The Alpha collaboration at CERN has achieved something that sounds like science fiction. They've created atoms of antihydrogen and held them long enough to study their properties. Each antihydrogen atom consists of an antiproton nucleus orbited by a positron, creating the antimatter equivalent of the universe's most common element. These antiatoms exist in a quantum state of perfect isolation, never touching any material surface, suspended in magnetic bottles while scientists probe them with laser light. The precision of these experiments reveals the profound symmetry between matter and antimatter. When antihydrogen atoms absorb light, they produce spectral lines that match theoretical predictions with extraordinary accuracy. The energy required to excite an antihydrogen atom from its ground state to its first excited state differs from that required for ordinary hydrogen by less than 2 parts in 10 billion. This level of precision tests one of the fundamental assumptions of modern physics, that antimatter atoms behave exactly like matter atoms, just with all charges reversed. But here's where the quantum mirrors reveal something disturbing about the nature of reality. According to the CPT theorem, one of the most fundamental principles in theoretical physics, antimatter should behave exactly like matter when observed in a mirror that simultaneously reverses all charges, spatial coordinates, and the direction of time. This theorem is so central to our understanding of physics that its violation would require us to rebuild our entire theoretical framework from the ground up. Yet the universe clearly violates this symmetry on cosmic scales. We exist in a cosmos dominated by matter, not antimatter, despite starting from conditions that should have produced them in exactly equal amounts. This means that somewhere in the laws of physics, subtle asymmetries exist that favor matter over antimatter in ways we don't yet understand. The search for these asymmetries has led to some of the most precise measurements in the history of science. Researchers have compared the masses of protons and antiprotons to 14 decimal places. They've measured the magnetic properties of both particles with extraordinary precision. They've studied how quickly different types of particles decay, and whether matter particles decay any differently than their antimatter counterparts. These experiments have revealed tiny but measurable differences in how nature treats matter and antimatter. Certain particles, called neutral kaons, can spontaneously transform into their own antiparticles and back again, but they don't do so symmetrically. The transformation from particle to antiparticle occurs slightly more readily than the reverse transformation. This asymmetry is incredibly small, a difference of just a few parts in 1,000, but it's real and measurable. The discovery of CP violation in kaon decay earned James Cronin and Val Fitch the 1980 Nobel Prize in Physics, but it also opened a profound mystery. The asymmetries they measured are far too small to explain the billion-to-1 dominance of matter over antimatter in today's universe. If kaon decay asymmetries were the only source of matter-antimatter imbalance, the universe should still be almost perfectly balanced between the two, with only tiny pockets of matter excess scattered throughout a cosmos dominated by annihilation radiation. This realization has forced physicists to search for additional sources of CP violation, mechanisms that could amplify the tiny asymmetries observed in particle decay into the massive imbalance we see on cosmic scales. The most promising candidate involves the Higgs field, the energy field that permeates all of space and gives particles their mass. In the early universe, when temperatures were billions of times hotter than anything we can create on Earth, the Higgs field may have existed in a very different configuration than it does today. As the universe cooled and the Higgs field underwent a phase transition, similar to how water vapor condenses into liquid, it might have created temporary conditions that favored the production of matter over antimatter. This process, called baryogenesis, could have occurred during a period when the universe was only a tiny fraction of a second old. The Higgs field transition would have created regions of space where the normal rules of particle physics were temporarily suspended, allowing processes that violate CP symmetry to operate on a cosmic scale. These processes could have converted a small fraction of the universe's antimatter into matter, creating the imbalance we observe today. But testing this theory requires recreating conditions from the first moments after the Big Bang, something That pushes our technology to its absolute limits. The Large Hadron Collider can achieve temperatures and energies that approach those of the early universe, but only for incredibly brief moments in tiny volumes of space. Whether these conditions are sufficient to observe baryogenesis in action remains an open question. The quantum mirrors of antimatter research have revealed that the universe operates according to rules far more subtle and complex than we initially imagined. Perfect symmetry, the aesthetic ideal that guided physics for centuries, appears to be fundamentally wrong. Reality is built on asymmetries so delicate that they can only be detected with the most sophisticated instruments humans have ever constructed. These discoveries force us to confront uncomfortable questions about the nature of existence itself. If the laws of physics contain built-in preferences that favor matter over antimatter, what other asymmetries might exist that we haven't yet discovered? Could there be entire categories of physics that remain hidden from us because they operate in regimes of energy and time that we cannot access? The quantum mirrors of matter and antimatter reflect images that are almost perfect, but not quite. Those tiny imperfections, those subtle violations of what should be perfect symmetry, appear to be the reason anything exists at all. We are the children of cosmic asymmetry, living in a universe that survived its own birth only because the laws of physics are beautifully, mysteriously, and perhaps accidentally imperfect. The more precisely we study antimatter, the more we realize how precarious our existence really is. We inhabit a cosmos balanced on asymmetries so subtle that they're measured in parts per billion, yet so crucial that without them, nothing we know or love would exist. The quantum mirrors show us reflections that are almost identical to ourselves, but that tiny difference makes all the difference in the universe. Chapter 5. Vanishing Universe. Picture this. You're standing in a vast library containing every book that has ever been written, every story ever told, every piece of human knowledge ever recorded. Now imagine that this library should actually contain two identical copies of everything, one written in regular ink, one written in antimatter ink that glows with otherworldly light. But when you look around, you see only books written in ordinary ink. Every antimatter volume has vanished, leaving behind only empty shelves and the faint radiation signature of annihilation. This is the cosmic library we inhabit. The universe should contain roughly equal amounts of matter and antimatter, like paired volumes in a cosmic collection. Instead, we find ourselves surrounded by matter alone, with antimatter existing only as a theoretical shadow of what should have been. The antimatter universe has vanished so completely that we can barely detect traces of it anywhere in the cosmos. The scale of this vanishing act defies comprehension. If the Big Bang had produced equal amounts of matter and antimatter, as our understanding of particle physics suggests it should have, then approximately half of all the mass energy in the universe today should exist in antimatter form. We're not talking about small amounts. The missing antimatter would have a total mass equivalent to hundreds of billions of galaxies, each containing hundreds of billions of stars. Where did it all go? The most straightforward answer is that it annihilated with an equal amount of ordinary matter, converting both substances into pure energy. But this explanation creates a paradox even more disturbing than the original mystery. If matter and antimatter were produced in exactly equal amounts and then annihilated completely, nothing material should exist in the universe today. We should inhabit a cosmos filled with nothing but radiation, photons carrying the energy released from the primordial annihilation, slowly cooling as space itself expands. Yet here we are, constructed from matter that somehow survived this cosmic holocaust. This survival requires that matter must have outnumbered antimatter from the very beginning, but only by the smallest possible margin. Current calculations suggest that for every billion antimatter particles created in the Big Bang, there must have been 1,000,001 matter particles. That single extra particle in every billion represents the entirety of the visible universe today. Think about what this means. Every atom in your body is a survivor of the most efficient destruction process known to physics. Every star, every planet, every grain of cosmic dust exists only because it was part of that tiny fraction of matter that had no antimatter partner to annihilate with. We live in the remnants of a universe that destroyed itself with near-perfect efficiency, leaving behind only the smallest possible residue of existence. But the vanishing doesn't stop with the primordial universe. Even today, antimatter continues to disappear from the cosmos almost as quickly as it's created. High-energy cosmic ray collisions routinely produce antimatter particles, but these particles survive only briefly before encountering matter and annihilating. The universe has become so thoroughly dominated by matter that antimatter cannot exist in any significant quantities anywhere we can observe. This ongoing disappearance has profound implications for our understanding of cosmic evolution. In a perfectly balanced universe, regions dominated by matter and regions dominated by antimatter would exist in a kind of cosmic segregation, separated by boundaries where annihilation occurs. These boundaries would glow with characteristic gamma radiation as matter and antimatter from opposite sides encounter each other and mutually destruct. Astronomers have searched extensively for such annihilation boundaries. Our most sensitive gamma-ray telescopes have mapped the entire sky, looking for the distinctive energy signatures that would mark the frontiers between matter and antimatter domains. They find nothing. The absence of annihilation boundaries provides compelling evidence that no significant antimatter structures exist anywhere within billions of light-years of Earth. The vanishing extends even to the smallest scales. In quantum field theory, particle-antiparticle pairs are constantly being created and destroyed in the vacuum of space itself. These virtual particles exist for such brief moments that they cannot be directly observed, but their effects can be measured with extraordinary precision. Even at this fundamental level, the universe seems to prefer matter over antimatter, though by margins so small they can only be detected in the most sophisticated experiments. This preference becomes visible in the behavior of certain unstable particles called neutral mesons. These particles can transform spontaneously into their own antiparticles and back again, oscillating between matter and antimatter states. But the oscillation isn't perfectly symmetric. The transformation from particle to antiparticle occurs slightly more readily than the reverse transformation, creating a subtle but measurable bias toward matter. The discovery of this asymmetry earned its discoverers the Nobel Prize, but it also deepened the mystery of the vanishing universe. The asymmetries measured in laboratory experiments are far too small to explain the complete dominance of matter over antimatter on cosmic scales. If particle decay asymmetries were the only mechanism favoring matter, the universe should still contain significant amounts of antimatter, distributed in regions too distant for us to observe directly. But the cosmic evidence suggests otherwise. Studies of the cosmic microwave background radiation, the afterglow of the Big Bang itself, show no evidence for the kind of large-scale matter-antimatter segregation that would be expected if both substances existed in significant quantities. The temperature variations in this ancient radiation indicate that the early universe was remarkably homogeneous, with no signs of the complex structure that would arise from matter-antimatter boundaries. This homogeneity implies that the matter-antimatter asymmetry was established very early in cosmic history, probably within the first second after the Big Bang. During this crucial period, some unknown process systematically converted antimatter into matter, or perhaps preferentially destroyed antimatter while preserving matter. The vanishing universe scenario suggests that this process was extraordinarily efficient, eliminating virtually all antimatter while leaving just enough matter to create everything we see today. The implications are both beautiful and terrifying. Beautiful because the process was so precisely calibrated. Too little matter survival and no complex structures could form. Too much, and the universe would have been dominated by matter from the beginning with no interesting physics occurring during the annihilation epoch. Terrifying because it suggests our existence depends on mechanisms we don't understand, operating during conditions we can barely imagine, producing outcomes that seem almost impossibly fine-tuned. Consider the alternative scenarios. In a universe where matter and antimatter remain perfectly balanced, constant annihilation would have prevented the formation of atoms, molecules, stars, and planets. In a universe where the asymmetry favored antimatter instead of matter, we would not exist to observe anything. In a universe where the asymmetry was too large, matter would have dominated so completely that the interesting physics of the annihilation epoch would never have occurred, possibly preventing the formation of the light elements necessary for complex chemistry. We appear to inhabit the one type of universe where the vanishing of antimatter proceeded at exactly the right rate to allow our existence. This realization forces us to confront questions about whether our universe is special, whether its properties are somehow inevitable, or whether we're simply lucky survivors in a cosmos where most possible outcomes lead to sterile, lifeless expanses of radiation. The vanishing universe represents more than just a missing piece of the cosmic puzzle. It represents the erasure of an entire shadow reality that should exist alongside our own. Somewhere in the universe's history, an antimatter cosmos full of anti-star, anti-planets, and perhaps even anti-life was systematically destroyed, leaving behind only the matter universe we inhabit today. We are the sole witnesses to one of the most complete disappearing acts in the history of the cosmos. The universe has vanished so thoroughly that we can only infer its former existence through the subtle asymmetries embedded in physical law and the lonely testimony of the matter that somehow survived to tell the tale. Chapter 6. Energy Prison. Every second, your body is bombarded by thousands of antimatter particles. They're created in the upper atmosphere when cosmic rays collide with air molecules, cascade down through the sky, and pass right through you as if you weren't there. Most of these particles are muons and their antimatter counterparts, traveling at nearly the speed of light and carrying enough energy to penetrate miles of solid rock. Yet despite this constant antimatter shower, you remain completely unaware of their presence. This invisibility reveals one of the most profound aspects of antimatter's rarity. Even when antimatter particles are created naturally through high-energy processes, they exist in what physicists call an energy prison, a state where their enormous potential for destruction is locked away by the very conditions that created them. The antimatter raining down from cosmic ray collisions carries energies thousands of times greater than the particles around them, making interaction extremely unlikely, despite the devastating consequences when such interactions occur. Understanding this energy prison requires grasping a fundamental principle of particle physics. Particles can only interact efficiently when their energies are closely matched. When a high-energy antimatter particle encounters the low-energy matter of your body, it's like trying to stop a speeding bullet with a spider web. The particle simply passes through without significant interaction, carrying its annihilation potential unused into the earth below. But when energies do match, when antimatter encounters matter at similar energy levels, the result is the most violent process known to physics. The entire mass of both particles converts to pure energy in a flash of gamma radiation so intense it can be detected from space. This is the energy prison's cruel irony. Antimatter carries the potential for perfect energy conversion, but that potential can only be unlocked under very specific conditions. Consider what happens during positron emission tomography, or PET scans, used routinely in hospitals around the world. Patients are injected with radioactive isotopes that decay by emitting positrons, antimatter electrons. These positrons carry relatively low energies, just enough to travel a few millimeters through tissue before encountering electrons and annihilating. Each annihilation produces two gamma rays traveling in exactly opposite directions, allowing medical scanners to track biological processes with extraordinary precision. The PET scan represents humanity's most practical use of antimatter's unique properties. The antimatter is created on-site using small particle accelerators called cyclotrons, which bombard stable isotopes with protons to create radioactive variants that undergo positron decay. The entire process, from antimatter creation to annihilation to medical imaging, occurs within hours, demonstrating how quickly antimatter must be used once it's produced. But scaling up this process to useful quantities of antimatter reveals the true nature of the energy prison. Creating just 1 gram of antimatter would require more energy than the entire United States produces in several years. Current production rates at the world's most advanced facilities measure in the nanograms per year, amounts so small they are essentially invisible even under powerful microscopes. At these rates, producing enough antimatter to power a spacecraft would require thousands of years using our most efficient production methods. The energy prison operates on multiple levels. First, creating antimatter requires enormous energy inputs, typically thousands of times more energy than the antimatter ultimately contains. Second, storing antimatter requires sophisticated magnetic confinement systems that consume continuous power to maintain the fields needed to prevent annihilation. Third, any practical use of antimatter requires converting its energy into useful work, a process that, like all energy conversions, suffers from significant efficiency losses. These constraints mean that antimatter, despite being the most energy-dense substance possible, remains trapped in a paradox of impracticality. The energy required to create it vastly exceeds the energy it can provide, making it useless as a power source using current technology. Antimatter becomes a perfect battery that costs more to charge than it will ever deliver. Yet the energy prison may not be permanent. Advanced civilizations might develop production methods that don't rely on the brute force particle acceleration techniques we use today. Some theoretical approaches involve capturing antimatter that occurs naturally in cosmic processes, though this would require technologies far beyond our current capabilities. Other proposals suggest using the intense magnetic fields around rotating neutron stars or black holes to separate matter and antimatter more efficiently than earthbound accelerators. The energy prison also explains why antimatter weapons remain firmly in the realm of science fiction. Despite antimatter's reputation for explosive power, the practical challenges of production, storage, and weaponization make it far less threatening than nuclear weapons. A nuclear bomb uses existing materials and well-understood engineering. An antimatter bomb would require producing and containing the most dangerous substance in the universe using technologies that barely work in laboratory settings. But perhaps the most significant aspect of the energy prison is how it reveals the universe's fundamental preference for matter over antimatter. In a perfectly symmetric cosmos, matter and antimatter would be equally common, making antimatter production unnecessary. We would mine antimatter from antimatter asteroids, just as we mine metals from ordinary asteroids today. The energy prison exists precisely because we live in a matter-dominated universe where antimatter must be artificially created rather than naturally harvested. This artificial creation process highlights another layer of the energy prison: conservation laws that govern how antimatter can be produced. Creating antimatter always requires creating an equal amount of matter simultaneously, meaning that antimatter production doesn't actually increase the universe's total matter content. It simply converts energy into balanced matter-antimatter pairs. The energy cost of this conversion, combined with the inevitable annihilation that follows, makes antimatter production a fundamentally energy-losing proposition. The energy prison extends into space, where cosmic antimatter faces similar constraints. When high-energy cosmic rays produce antimatter particles in interstellar space, these particles typically carry so much energy that they interact very weakly with the low-energy matter around them. They can travel for thousands of years through the galaxy before encountering matter with matching energy levels and finally annihilating. This creates a cosmic version of the energy prison, where antimatter exists in isolation not because it's physically separated from matter, but because it exists in a different energy regime. The universe contains far more antimatter than we typically realize, but most of it is locked in high-energy states that make interaction with ordinary matter extremely unlikely. Breaking out of the energy prison would require mastering technologies that border on the impossible. We would need to develop production methods that approach perfect efficiency, storage systems that operate without energy loss, and applications that could harness antimatter's energy with near-perfect conversion rates. Even if such technologies were possible, they would represent engineering challenges that dwarf anything humanity has ever attempted. Yet the energy prison also represents an opportunity. If we could develop even modest improvements in antimatter production and handling, the energy density advantage over conventional fuels would be so enormous that spacecraft powered by antimatter could reach nearby stars within human lifetimes. The key insight is that we don't need to break out of the energy prison completely. We just need to make it slightly more porous. The energy prison that contains antimatter is ultimately a reflection of the universe's deep structural asymmetry. In a matter-dominated cosmos, antimatter will always be the outsider, the exotic substance that requires enormous effort to create and constant vigilance to contain. We are prisoners alongside our antimatter, trapped in a universe where the most powerful energy source imaginable remains forever just beyond our practical reach. Chapter 7. Broken Time in 1964. Two physicists working with particles called neutral kaons made a discovery so disturbing that it threatened to undermine one of the most fundamental assumptions about the nature of reality. James Cronin and Val Fitch found that time itself can flow backwards at the quantum level, not just theoretically, but measurably, repeatably, and in ways that violate what physicists believed were inviolable symmetries of nature. Their discovery centered on a particle that seems designed to test the limits of what is possible in physics. Neutral kaons are peculiar creatures that can spontaneously transform into their own antiparticles and back again, oscillating between matter and antimatter states like quantum chameleons. According to every theoretical framework that physicists had developed, this transformation should be perfectly reversible. If you filmed the kaon transforming into its antiparticle and played the film backwards, the backwards version should represent an equally valid physical process. It doesn't. The transformation from particle to antiparticle occurs more readily than the reverse transformation, creating an asymmetry so subtle that it can only be detected in the most carefully controlled experiments. This asymmetry represents something far more profound than just another quirky behavior of subatomic particles. It means that the fundamental laws of physics can distinguish between forward and backward time. To understand why this matters for antimatter's rarity, imagine watching two movies. In the first, matter and antimatter are created in equal amounts during the Big Bang, and then evolve forward in time according to physical laws that treat both substances identically. In this movie, the universe should remain perfectly balanced between matter and antimatter for all eternity. In the second movie, you watch the same process, but with time running backwards. If the laws of physics are truly time-symmetric, both movies should look equally plausible. But Cronin and Fitch's discovery proved that the second movie would look wrong. The subtle asymmetries they measured in kaon decay mean that certain physical processes have a preferred direction in time. They occur more readily when time flows forward than when time flows backward. This temporal preference, though incredibly small, could accumulate over cosmic timescales to create the matter-antimatter imbalance we observe today. The mechanism behind broken time symmetry involves one of the strangest concepts in quantum mechanics: particle mixing. Neutral kaons exist in quantum superposition states where they are simultaneously both matter and antimatter until the moment they reobserved or interact with other particles. During this superposition, they can decay through multiple pathways, each with slightly different probabilities. The asymmetry arises because the decay pathway that produces matter particles is very slightly favored over the pathway that produces antimatter particles. This preference is almost impossibly small. The asymmetry in kaon decay amounts to just a few parts in 1,000, so tiny that it took decades of experimental work to measure it reliably. Yet this minuscule violation of time symmetry was the first concrete evidence that the laws of physics contain built-in preferences that could, in principle, explain why matter dominates over antimatter in our universe. The discovery earned Cronin and Fitch the 1980 Nobel Prize in Physics, but it also opened up one of the most profound mysteries in modern science. If time symmetry can be broken at the level of particle decay, what other fundamental symmetries might be violated in ways we haven't yet discovered? And more importantly, are these violations sufficient to explain the billion-to-one dominance of matter over antimatter that we observe on cosmic scales? The answer to this second question has proved disappointing. While the asymmetries measured in kaon decay are real and measurable, they're far too small to account for the complete absence of antimatter in today's universe. If broken time symmetry in kaon decay were the only mechanism creating matter-antimatter imbalance, the universe should still contain roughly equal amounts of both substances, with only tiny regions showing slight preferences for matter over antimatter. This realization has forced physicists to search for additional sources of time symmetry breaking, processes that could amplify the tiny asymmetries observed in laboratory experiments into the massive imbalance we see on cosmic scales. The leading candidates involve particles and processes that existed only in the first moments after the Big Bang, when the universe was so hot and dense that entirely different physical laws may have been in operation. One possibility involves the Higgs mechanism, the process that gives particles their mass. In the early universe, when the Higgs field underwent its phase transition from a high-energy state to its current low-energy configuration, it may have created temporary conditions where time symmetry breaking could occur on a cosmic scale. During this transition period, lasting perhaps a billionth of a second, the normal rules of particle physics would have been suspended, allowing processes that massively favor matter over antimatter production. Another possibility lies in the realm of grand unified theories, which attempt to describe all fundamental forces as aspects of a single, more fundamental interaction. These theories predict the existence of extremely massive particles that would have been produced in abundance during the Big Bang but decayed quickly as the universe cooled. If these particles decayed asymmetrically, preferentially producing matter over antimatter, they could have created the imbalance we observe today. The broken time symmetry observed in kaon decay provides a proof of principle that such asymmetric processes can occur, but the challenge lies in finding mechanisms powerful enough to operate on cosmic scales. The time symmetry violations measured in laboratory experiments are like whispers compared to the cosmic shout that would be needed to explain antimatter's rarity. Recent experiments have extended the search for time symmetry breaking to other types of particles. The LHCb experiment at CERN has measured similar asymmetries in the decay of particles containing bottom quarks, finding violations of time symmetry that are larger than those observed in kaons, but still orders of magnitude too small to explain cosmic antimatter asymmetry. These measurements provide additional evidence that time symmetry breaking is a general feature of particle physics, not just a peculiarity of kaons. The study of broken time symmetry has also revealed something deeply unsettling about the nature of reality. The equations that describe fundamental particle interactions contain complex mathematical structures, where time can effectively flow backwards, where cause and effect become entangled, and where the distinction between past and future becomes meaningless. At the quantum level, time is not the steady, unidirectional flow we experience in our everyday lives, but rather a dimension that can be twisted, bent, and even reversed under certain conditions. This realization has profound implications for our understanding of causality and free will. If the fundamental laws of physics don't respect the direction of time, if particles can influence their own past states through quantum superposition, then the entire concept of linear causation may be an illusion created by our limited perspective on reality. We may be living in a universe where effects can precede causes, where the future influences the past, and where time itself is just another dimension that can be manipulated like space. The broken time symmetry that creates matter-antimatter asymmetry may be telling us that the universe operates according to principles that are fundamentally alien to human intuition. We evolved to perceive time as a one-way street, always flowing from past to future, always preserving clear distinctions between cause and effect. But the quantum world reveals time to be far stranger and more flexible than our evolutionary programming prepared us to understand. Perhaps the most disturbing aspect of broken time symmetry is how it reveals the contingent nature of our existence. We live in a universe where the fundamental laws of physics are slightly, almost imperceptibly broken in just the right way to allow matter to survive the annihilation that should have destroyed everything. If time symmetry had been preserved perfectly, if the tiny asymmetries in particle decay didn't exist, then matter and antimatter would have achieved perfect balance and mutual destruction. The broken time that allows our existence represents one of the deepest mysteries about why the universe is the way it is. We are the children of symmetry breaking, living in the aftermath of temporal imperfections so subtle that they can only be detected with the most sophisticated instruments ever built. Time itself appears to be fundamentally flawed, and those flaws are the reason we exist to contemplate them. Chapter 8. Hidden Dimensions. Imagine that our entire universe, every star, every galaxy, every particle of matter we can observe, exists on the surface of a soap bubble floating in a vast space we cannot perceive. Now imagine that surrounding this bubble are countless other bubbles, each containing its own universe with its own physical laws, its own distribution of matter and antimatter, and its own version of reality. Some of these parallel universes might be dominated by antimatter instead of matter. Others might achieve perfect balance between the two, annihilating themselves out of existence. And a few, like ours, might have just enough asymmetry to survive and evolve complexity. This is not science fiction. This is one of the leading theoretical explanations for why antimatter is so rare in our universe. String theory, the most ambitious attempt to unify all fundamental forces under a single mathematical framework, suggests that our familiar 3 dimensions of space and 1 dimension of time may be just a subset of a much larger, multidimensional reality. In this expanded cosmos, the apparent rarity of antimatter in our universe becomes not a fundamental mystery, but simply a local condition, one possibility among countless others playing out across dimensions we cannot access. The mathematics of string theory requires the existence of at least 10 dimensions, possibly 11 or even more. 6 or 7 of these dimensions must be compactified, curled up so small that we cannot detect them directly, while the remaining dimensions form the 4-dimensional spacetime we experience. But the way these extra dimensions are compactified determines the fundamental properties of physics in our observable universe, including the balance between matter and antimatter. Consider how this works. In the full multidimensional space of string theory, matter and antimatter may exist in perfect symmetry, with equal amounts distributed throughout the complete reality. But our 4-dimensional slice of this larger space might sample this distribution unevenly. Just as a 2-dimensional creature living on the surface of a multicolored sphere might see only blue paint while being unaware of the red paint on the opposite hemisphere, we might inhabit a region of the multidimensional cosmos where matter happens to dominate, even though antimatter dominates elsewhere. This explanation gains support from recent developments in cosmological theory. The multiverse concept suggests that the Big Bang was not a unique event, but rather one episode in an ongoing process of universe creation. In this framework, countless universes are constantly being born, each with slightly different physical properties determined by how the fundamental fields and dimensions configure themselves. Most of these universes would be sterile, dominated by radiation or achieving perfect matter-antimatter balance that leads to complete annihilation. But a few would develop the slight asymmetries necessary for matter to survive and complexity to emerge. The hidden dimensions might also explain why antimatter production is so energy-intensive in our universe. If antimatter naturally exists in abundance in dimensions we cannot access, then creating it in our four-dimensional space requires borrowing energy from these hidden dimensions, a process that might be inherently inefficient given the constraints of how dimensions interact. We would be like two-dimensional beings trying to extract objects from a three-dimensional space, finding the process inexplicably difficult because we cannot perceive the full context of what we're attempting. Some versions of string theory go further, suggesting that matter and antimatter might actually be the same substance viewed from different dimensional perspectives. Just as a cylinder appears circular when viewed from one direction and rectangular when viewed from another, matter and antimatter might be unified in the higher dimensions while appearing opposite in our limited four-dimensional view. This would mean that the rarity of antimatter in our universe reflects not a fundamental asymmetry, but rather a dimensional projection effect, like seeing only one side of a coin that exists in a space we cannot perceive. The implications extend far beyond particle physics. If our universe exists within a larger multidimensional space populated by other universes, then the antimatter missing from our cosmos might not be truly missing at all. It might exist in adjacent universes that we cannot observe or interact with directly. These antimatter universes would be running their own versions of cosmic evolution, perhaps developing their own versions of stars, planets, and even life, all constructed from substances that would annihilate instantly if they ever encountered our matter-dominated reality. But hidden dimensions also introduce disturbing possibilities for our own universe's future. If the configuration of extra dimensions can change over time, as some versions of string theory suggest, then the fundamental properties of physics in our universe might not be permanent. The asymmetry that currently favors matter over antimatter could shift, potentially triggering a cascade of changes that would alter the basic structure of reality itself. Some cosmologists have proposed that we might already be witnessing evidence of such dimensional shifts in the form of dark energy, the mysterious force causing our universe's expansion to accelerate. If dark energy represents leakage between dimensions, or changes in how the hidden dimensions are compactified, then it might be the first sign that our universe's fundamental properties are beginning to evolve. Such evolution could eventually restore perfect matter-antimatter symmetry, leading to a future epoch where our current matter-dominated cosmos annihilates itself. The search for evidence of hidden dimensions has become one of the most active areas of experimental physics. The Large Hadron Collider at CERN is designed to detect signs of extra dimensions by looking for particles that appear to vanish from our four-dimensional space, potentially escaping into higher dimensions. If such particles are found, they would provide the first direct evidence that our universe is embedded in a larger, multi-dimensional reality. Other experiments are searching for more subtle signatures of hidden dimensions. Measurements of gravity at very small scales might reveal deviations from Einstein's inverse square law if gravitational force can leak into extra dimensions. Astronomical observations of distant galaxies might show unexplained patterns that could be explained by gravitational influences from parallel universes existing in nearby regions of the multidimensional space. The concept of hidden dimensions also offers a potential solution to one of the most frustrating aspects of the antimatter mystery. While laboratory measurements of CP violation are so much smaller than what's needed to explain cosmic antimatter asymmetry, If the processes that created matter-antimatter imbalance operated partially in hidden dimensions, then we might only be observing the four-dimensional projection of much larger asymmetric processes. The full scope of the asymmetry would remain hidden from us, accessible only through its reduced effects in our observable space. But hidden dimensions also raise profound questions about the nature of scientific knowledge itself. If the fundamental properties of our universe are determined by configurations and dimensions we cannot perceive or explore directly, then there may be aspects of reality that remain forever beyond human understanding. We would be like inhabitants of a shadow world, seeing only the projections of a larger reality we can never fully comprehend. This limitation becomes especially troubling when we consider the implications for the future of physics. If antimatter's rarity is explained by hidden dimensional effects, then our entire approach to understanding fundamental physics might be fundamentally incomplete. We might be trying to solve a multi-dimensional puzzle using only four-dimensional tools, forever missing the crucial pieces that exist in spaces we cannot access. The hidden dimensions that might explain antimatter's rarity represent both the greatest hope and the greatest fear of modern theoretical physics. Hope, because they offer elegant mathematical frameworks that could unify all known forces and explain the deepest mysteries about why our universe has the properties it does. Fear, because they suggest that reality might be so much larger and stranger than we imagined in our human perspective. No matter how sophisticated our instruments become, we'll always remain fundamentally limited. We may be living in a universe whose most important properties are determined by dimensions we cannot see, processes we cannot observe, and symmetries that exist only in mathematical spaces beyond our perception. The missing antimatter that should fill our cosmos might not be missing at all. It might be hidden in plain sight, existing in dimensions that remain forever beyond our reach, governing our reality from spaces we can never explore. Chapter 9. Universal Accident. There's something deeply unsettling about the possibility that your existence and everything else that has ever existed might be the result of an accident so improbable that it should never have occurred at all. Yet as we peer deeper into the fundamental structure of reality, this disturbing possibility becomes increasingly difficult to dismiss. The rarity of antimatter in our universe may not be the result of elegant physical laws or inevitable cosmic processes, but rather the consequence of a quantum accident that occurred in the first billionth of a second after the Big Bang. Consider the odds. If matter and antimatter were produced in exactly equal amounts during the universe's birth, they would have annihilated each other completely, leaving behind nothing but radiation. If matter had dominated too strongly from the beginning, the universe would have been matter-dominated from the start, with no interesting annihilation physics occurring during its early evolution. The actual outcome, where matter outnumbered antimatter by exactly 1 part in a billion, falls into an incredibly narrow range that allows both complexity and existence. This is not the kind of fine-tuning that physicists find comfortable. In most areas of physics, the fundamental constants and initial conditions that govern natural processes span reasonable ranges, where small changes produce small effects. But the matter-antimatter asymmetry appears to require precise calibration at a level that suggests either extraordinary design or extraordinary luck. Since most physicists are reluctant to invoke design as an explanation for natural phenomena, we're left with the uncomfortable possibility that we're extraordinarily lucky. But what if luck isn't the right word? What if the accident that created our universe wasn't random but inevitable? Not because of physical laws, but because of the anthropic principle. This controversial idea suggests that we observe a universe with precisely the right matter-antimatter asymmetry, not because such universes are likely, but because we can only exist in universes with these properties. All the perfectly balanced universes where matter and antimatter annihilated completely remain forever unobservable because they contain no observers. The anthropic principle offers a disturbing resolution to the antimatter mystery, but at a philosophical cost that many find unacceptable. It suggests that the fundamental properties of our universe are not determined by elegant physical laws, but by the simple requirement that those properties be compatible with our existence. The universe doesn't have the properties it has because they're inevitable or beautiful or mathematically preferred. It has these properties because if it had different properties, we wouldn't be here to observe them. This explanation requires accepting that we live in a multiverse, an ensemble of countless universes with different physical properties, most of which are sterile and lifeless. In this vast cosmic lottery, universes with perfect matter-antimatter balance destroy themselves through complete annihilation. Universes with too much matter asymmetry become dull and predictable. Only a tiny fraction develop the precise conditions necessary for complexity, chemistry, and consciousness to emerge. The accident that created our universe would thus be unremarkable in a cosmic sense. Among the countless universes being born in an eternal process of cosmic creation, accidents favoring matter over antimatter by just the right amount would occur regularly. They would be rare compared to the total number of universes, but inevitable given infinite attempts. We find ourselves in such a universe not because we're special, but because we can only find ourselves in universes where our type of accident has occurred. But the universal accident hypothesis faces serious challenges. Most versions of multiverse theory that could explain fine-tuning also predict that we should observe other types of evidence for our special status evidence that remains stubbornly absent. If our universe is fine-tuned for our existence, why don't we see signs of optimization in other cosmic properties? Why is the cosmological constant so close to zero, but not exactly zero? Why are the masses of fundamental particles what they are rather than values more conducive to complexity? The accident interpretation also struggles with the problem of probability. In an infinite multiverse, where all possible universes exist, every conceivable outcome occurs infinitely often. This makes it mathematically meaningless to say that our universe is improbable. Infinite multiverse models predict that we're equally likely to find ourselves in any universe compatible with our existence, regardless of how that universe achieved its life-friendly properties. Some physicists have proposed that the appearance of accident and matter-antimatter asymmetry might reflect deeper principles we don't yet understand. Perhaps what looks like fine-tuning to us represents the operation of physical laws that naturally produce life-friendly conditions. These laws might operate at energy scales or time scales far beyond our current experimental reach, creating what appears to be cosmic accident, but is actually cosmic inevitability. The search for such principles has led to some of the most speculative theories in modern physics. Loop quantum gravity suggests that the Big Bang wasn't the beginning of our universe, but rather a bounce from a previous universe that collapsed and then expanded again. In this model, the matter-antimatter asymmetry might have been inherited from the previous cycle, making it a legacy rather than an accident. String theory proposes that the fundamental properties of physics are determined by the shape of hidden dimensions, which might naturally configure themselves to produce life-friendly conditions. But these explanations simply push the accident back one level. If loop quantum gravity is correct, why did the previous universe have the properties necessary to produce our matter-antimatter asymmetry? If string theory is correct, why did the hidden dimensions have the shapes that produce life-friendly physics rather than sterile mathematics? At some level, the appearance of design or accident in our universe's properties seems unavoidable. The universal accident interpretation also raises profound questions about meaning and purpose in the cosmos. If our existence is the result of an improbable quantum fluctuation that occurred for no deeper reason than random chance, then the universe contains no inherent meaning or direction. We are not the inevitable products of cosmic evolution, but rather accidental byproducts of processes that could just as easily have produced nothing at all. This perspective can be either liberating or terrifying, depending on your philosophical inclinations. Liberating because it means that human consciousness and creativity are genuinely novel developments in cosmic history, not predetermined outcomes of fundamental laws. Terrifying because it means that everything we value, life, consciousness, love, art, science itself, exists only because of an accident so unlikely that it borders on the miraculous. The accident hypothesis also implies that our universe is far more fragile than we might hope. If the matter-antimatter asymmetry that allows our existence is the result of a delicate balance rather than robust physical laws, then small changes in cosmic conditions might be sufficient to destabilize everything. Dark energy, quantum vacuum decay, or dimensional phase transitions could potentially restore perfect symmetry to the universe, leading to a future epoch of complete annihilation. Perhaps the most disturbing aspect of the universal accident hypothesis is how it reveals the potential meaninglessness of the search for ultimate explanations. If our universe's properties are fundamentally accidental, then the entire scientific enterprise of trying to understand why things are the way they are might be based on a false premise. There might be no deep reason why antimatter is rare, why physical constants have their observed values, or why the universe is structured the way it is. We would be like archaeologists trying to understand the significance of patterns in rocks created by random erosion, forever seeking meaning in arrangements that are fundamentally meaningless. The beauty and elegance that physicists find in natural laws might be illusions created by our evolved tendency to see patterns even where none exist. The universe might be telling us no story at all because there is no story to tell. Yet even if our universe is the result of a cosmic accident, that accident has produced something extraordinary. Conscious beings capable of contemplating their own existence and asking questions about why they exist at all. Whether this consciousness emerged inevitably from cosmic laws or accidentally from cosmic chaos, it represents a development of staggering significance. We are the universe becoming aware of itself, accident or not. The universal accident that may have created our matter-dominated cosmos has given rise to something that transcends its origins. The capacity to wonder about those origins and to find meaning in the search for understanding, even if no ultimate understanding exists to be found.